I hope you all can hear me. Please let me know if you can hear me. I'm going to launch a poll, so please respond if you can hear me. It feels to me like that everyone can hear me. So we are again meeting with these basics of introduction to electrical power course. Earlier it was basics of electrical machines, and I hope that you all have gone through the LMS and got to know about the changes that has been made to this course. There were several changes in the intended learning outcomes or as the objectives of this course as well. So therefore, depending on that, the content was also changed. So I hope that you can simply go through the course plan and get to know what are the changes that were made, and at the same time the topics were accordingly changed in the LMS. So please go there and have a visit and get to know about the changes that has been done. Please let me know that if you cannot access the LMS for some reason, please let me know that that happened with your senior badge and I fixed the issues from my side. And in your case as well, if you have any issues regarding accessing the LMS, please let me know. And the changes that has been made, that were made to this course, were kind of updated there as well. Right. Last time we discussed, so now I'm going to share my screen with you, and I hope you all can see it. So last time we discussed about these topics, the categorization of machines. They were learned about the basic categories depending on the motion, depending on the right. Sorry for the kind of the inconvenience, and I couldn't mute you all from the beginning. So if you, for some reason, if you want to unmute yourself, please let me know. I have disabled the feature. You cannot unmute yourself. And so there we learned about these categories basically, and we got to know about the commonly used types of machines. Thereafter, we discussed about the basic construction of a machine. What are the main kind of important and generally you would find in the parts that you would generally find in a machine. So we discussed those things. And then we got to the last part, singly excited magnetic systems. Simply, it's like an electromagnet. So, or as a solenoid coil or relay, something like that. So where you are going to have only one current carrying coil and create a magnetic field around. So there we kind of had the insight, or as the started to discuss about this magnetic circuits. So today we are going to continue from there onwards, and we are going to extend the topic to multiple excited machines as well, right? And if we had enough time, we would try to discuss about these single loop DC motors. But I believe, as far as I got to know, that you have discussed this single loop basic construction of, or as the basic construction of the DC motor in the first year as well. So I hope that therefore it is not going to be that much problematic. So before going to the magnetic circuits, I would like to kind of refresh your memory from the beginning about the magnetism, and therefore and kind of make you recall the important things that you should know in order to understand the magnetic circuits. So let's start today's discussion. So as you already know, so magnets have special ability to kind of repel or attract depending on the type of the poles. So first thing is that we define something known as magnetic flux, which is residing around the magnet. And what you need to know is that this magnetic flux is always coming out from the north pole and going in from the south pole. And they are always uh, they are as closed paths, right? In other words, you won't see magnetic flux which is not ending from a south pole, right? So all the time it's going to end somewhere in a south pole and begin from north pole by convention. That's something we define, right? In order to kind of make it easier to explain the things happening with magnets, right? And the other thing you should know is that it's not just a two-dimensional, like shown in this case. Instead, it's a three-dimensional distribution. So, in other words, the flux is distributed in all direction, not only in one plane. Instead, it's consuming the entire volume around the magnet, right? And no matter how hard you would try, if you break this magnet apart to two pieces, you would again end up with two magnets, which each having two poles. In other words, you cannot have a magnet which only has a north pole or either only a south pole. So always magnets come as a pair of poles. And you know already that the like poles are repelling, and dislike poles are attractive. So those things I believe you know. And the other thing I want to mention here in this graph is that if you observe the flux distribution, right? When you go closer to the magnet, the number of flux lines are increased. And as you go further, the number of flux lines decrease. So which means if you consider an area of unit area closer to the magnet itself, the magnetic flux density is higher there. And if you go further away from the magnet and measure the magnetic flux density, so you already know that magnetic flux density means the amount of flux which is perpendicularly going through a considered area. And if you go further away from the magnet, this density would decrease. So that you should know. And in this case, you can clearly see if the magnetic flux density here is B1 and the density here is B2, B1 is higher than B2. And of course, you know that magnetic flux density means magnetic flux divided by the area, or else magnetic flux is equal to flux density multiplied by the area. For an instance, if you want to know the total flux going through this plane here, what you have to do is you have to multiply the magnetic flux density in this area by the area itself, then you get the flux amount, right? So in this case, we assume that everywhere the flux density is a constant. If it is not a constant, for an instance, at this corner, if the flux density is higher compared to this other corner, what you have to do is you have to use the continuous form of integration. In other words, continuous form equation, which is going to integrate the flux density from the area, right? And so in that case, you have to use this equation. But in our course, we are not going to use these continuous form equations. One reason is it's not needed unless you are going to design something. So for our understanding, we're just going to go with this simple equation. So where we assume that the flux density is constant. So in most of the cases, in the electrical machines, it's possible to assume that the magnetic flux density is constant because they are in most cases they are rotating machines. So the other thing is the magnetic flux magnetic field intensity, which we denote by the capital letter H. Sometimes it is the same is called as magnetizing force. So again, for a magnet like this, permanent magnet like this, intensity will be higher when you go closer and be lower when you go further away from the magnet, right? So those basics you should be already familiar with. And the next thing is about the how a current can give rise to a magnet. So you know that if conductor is carrying electrical charge through it, so what would happen is, by convention, if you point your thumb to the direction of the current flow, the fingertips of your other fingers would give the direction of the magnetic flux, right? So this you already know, which is the right hand rule. And it is when it comes to kind of calculations, or as when deciding the directions. So you know that we draw these diagrams not three-dimensional like shown in this graph, this image here. Instead, we use some notations. So you know that we use these cross and dot notations for both current and magnetic field. So in this case, you can see the current is going down and the magnetic field is denoted by using this dot and cross convention. Here, the current is going into the board or as the screen, and the magnetic flux is shown. So this notation you should be familiar, right? So again, from the first year, you know these things. Therefore, I'm not going to waste your time. And the other thing you should know is the Ampere's law. So the basic relationship between the intensity, right, and the current. So field intensity and the current. So what it relates is, for an instance, if you consider this closed loop here, right? So we can assume that the magnetic intensity is constant around the loop. So in that case, in order to find the magnetic intensity, what you have to do is you have to know the total current flowing within the loop, right? So I'm only talking about this outer loop, right? So since it is a kind of a circular path, we can assume H is constant everywhere. H is constant everywhere. So then what we have to do in order to know what H is, so you need to know what is the total current going through this conductor, right? So the current value you have to know. So if you know the current value, by Ampere's law, what it states that the net current value is equal to H multiplied by the this length of this entire circular path. So in this case, it is 2 pi r. The length of this path is 2 pi r. So let me use a different color for that length. It's going to be 2 pi r. So this is the radius, right? So when you multiply it, the length value by the H, that is going to be equal to the current, the total current actually. Therefore, that's why we are net current value. That's why we are using sigma there, right? Sigma I. So the same in the same kind of scenario in the continuous form is denoted as shown here, right? So this equation simply means the reveals the general case of Ampere's law. So what it states, in other words, is, so in this case, we assume that the magnetic field intensity is constant, but for a considered closed path. So in this case, this is a closed path, right? So for a considered closed path, so the magnetic field intensity at a given point, for an instance, the intensity here may be H1, and a point like this, the intensity would be different, H2. So for a situation like that, in order to find the relationship between the current and the magnetic field intensity, what you have to do is you have to sum up or as they take the net value of all the current. So that's what we have done here. So I1 and I2 is in the same direction, therefore they are adding, and I3 is in the opposite direction, so therefore it is minus. So you have to sum up all the currents, and then you consider a small distance of delta H, DL, right? So DL in this case is a small distance. And then you are going to take the dot product of magnetic field intensity. So you may not know what dot product is. So simply it's a type of vector product, uh, and you don't need to worry about that at this moment. So you take this smaller dl vector and the magnetic field intensity vector at that point, and you take the dot product of that. So the only thing that is happening when you take the dot product is you're going to multiply the magnitude of magnetic field intensity and the magnitude of the dl distance and take the cos value of the angle between them, right? So just you don't have to worry about this. We are not going to do calculations using this one. So it's just for you to get to know that there is something like that. And now what we are doing here is, by this notation, it means simply, so I'm basically telling this, you are going to do this multiplication for smaller distances, right? Smaller distances along the entire path, right? Entire path. And remember that it has to be a closed path. That's why this circle is there. So this is a closed path. Here again as well, it is a closed path. So this law here is only for closed paths, right? So basically that you should understand. What you should understand here is that there is a relationship between the current and the magnetizing force, or else magnetic field intensity, right? And so this is just a current carrying conductor. So what would happen when you are going to make a coil with that one? So that's what you see here. So this is a copper coil, and if you are going to give electromotive force, there would be a current through this coil. So in this case, what would happen is it would give rise to a magnetic field, right? So if you apply the known rules here, right, you can get to know that this current, in other words, if the current would flow in this direction, it would give rise to a magnetic field like this, right? And this magnetic field, which is created from the current carrying coil, is not that different from the permanent magnetic field. So as you can see, so it's same as a permanent magnet, but the only thing is you can control the magnetic field by using the current, right? So the intensity, or as the strength of the magnet, can be controlled by the current and the number of turns, right? So remember, this simply we call an electromagnet now, right? This is an electromagnet, and by using the current and the number of turns, right? Number of turns, you can control the strength of the magnetic field, right? If you increase the current value, the strength would increase. And if you, so that relationship, why is it going to increase? So because the relationship between the magnetic field intensity and the net current value is kind of proportional if we assume the magnetizing force to be constant, right? and that's one thing. And depending on the number of turns, again this strength is going to increase, because if you increase the number of turns, what you are doing here is basically you are increasing the net value, net current value. So because the in this case, if you consider, since there are 1 2 3 4 5 6 7 8 turns, so the current coming through this conductor is multiplied by 8. It's, in other words, it's going to be added 8 times, right? So it's like I plus I, something like that, and 8 times. So simply it is the multiplication of number of turns. In other words, what you are going to do here is you are going to multiply I by the number of turns. So in this case, it is 8, right? And so, right, I assume it's clear so far. So do you have any question so far? If you have any questions, I would like to answer now. Do you have any questions? You can send your questions through the chat box. Right. Seems like no one has questions, so we're going to continue. And the next thing is the relationship between B and H, right? So the relationship between B and H. So you know B is the magnetic flux density, H is the magnetic field intensity. So this I can clearly explain with an example like this. So let's say you're going to put your electromagnetic coil in water and air, right? So when you put it water and give the same current, let's say I. So for an instant, let's say that in this case, it's 10 amperes. Here as well, it's 10 amperes. So now, by according to the Ampere's law, if you consider a point which is distance away from the coil and in the same direction, so by Ampere's law, you can prove that the magnetic field intensity, right? Magnetic field intensity is only dependent on this current. The number of turns is the same for both scenario, and the current is same. Therefore, magnetic field intensity should be same for both scenarios. In other words, when you put your electromagnet in air at a point, and remember this magnetic field intensity is defined for a point at space, in space, right? So this H is defined for a point in space. It's not a property of the magnet, but directly related to the magnet. So if you take another point, the magnetic field intensity would be different. And if you take a point farther away, it's again different value, right? So those things I believe you already know. And now what I want to tell here is that if you consider the same point, right, which is away from the same distance away from the magnet, the magnetic field intensity should be the same, because the current is the same value, 10 amperes, and the number of turns are the same, right? It's eight turns, right? Yeah, so it's 8, right? Therefore, the total or as net current value is 80 amperes. 80 amperes. So therefore, the magnetic field intensity should be the same. But if you think of the magnetic flux density at this point, right? Magnetic flux density at this point, when you compare the water and air, it's not the same. They are going to have different values. If I say for water it's BW and for air it's BA, BW is not going to be equal to BA, right? But if I name these magnetic flux intensities as HW and HA, HW is equal to HA. So what you should understand here is that both magnetic flux density and magnetic flux magnetic field intensity is defined for a point in the space which is residing in a magnetic field, right? Magnetic field that ඇතුළේ තියෙන point එකට තමයි මේ දෙකම define කරලා තියෙන්නේ. ඒතකොට point එකෙන් point එකට වෙනස් values එන්න පුළුවන් මේවට. හැබැයි when you consider about the same point, so the same point which is especially locating from the same distance and same direction away from the magnet or within the magnetic field, the magnetic field intensity could be the same, but magnetic flux density is different, right? Because this is depending on the medium. Magnetic flux density depends on the medium. So if you use a different medium other than water and air, the flux density would be a different value. But still the magnetizing force or as the magnetic flux magnetic field intensity H is the same, right? And another thing I want to mention here is the net current value for a situation like this, uh, by as a kind of a thumb rule or as a not a kind of a metric unit, though it is not a metric unit, sometimes you name as ampere turns, right? A capital T, right? A capital T. So the reason is ampere turn, capital T or simple T. Sometimes people use simple T as well. And the reason is to give the idea that this is not the current through the coil, right? Current through the coil is 10 ampere, but the net current value is current through the coil multiplied by the number of turns of the coil. So to give the idea that this is the net current, right? And we will give it a different name in the next few theories to come in this lecture. We will give a different definition for this ampere turns amount. And I hope that's very much clear, the difference between the magnetic field intensity and the magnetic flux density, right? And going further, if you let's say, okay, you are going to insert a different medium here, so it's in the air and you are going to have a piece of, let's say, metal, cast steel or silicon steel metal with through this coil, right? So when you insert this steel or whatever plate within the coil, into the coil, uh, the flux would be generated there, right? So there would be magnetic flux going through this coil, right? In this case, I assume, okay, the current is flowing in the opposite direction, and likewise, the magnetic field is generated. Now, again, if you consider just this is cast iron, right? This is cast iron plate. What would happen is, due to this current and the number of turns, it would have some sort of a magnetizing force or as magnetic field intensity in the coil, which is not dependent on the medium, right? So that intensity, let's say, okay, for a given time is 200, right? 200. And if you if you include for a given time, it's 200, I assume, right? Now, if you are going to insert a cast iron steel, what would happen is you would get a magnetic flux density of 0.1, right? And instead, if you insert a cast steel, right? So instead of a cast iron, you are going to insert a cast steel plate. Now what would happen is you would get, because magnetic field intensity is not changing, it's only changed, it can only be changed by the current and the number of turns. So it's not going to change. Now at this situation, what would happen is you would get a different magnetic flux because the medium was changed. The material made of material which is made from of this steel was changed. So now you get a different magnetic flux density, which is 0.2 Tesla, right? And magnetic flux density. And instead of both this cast steel and cast iron, if you include a plate made of silicon sheet steel, you would get a really high amount of magnetic flux, which is 1 Tesla, right? So what I want to tell is that there are materials, right, which can give a very high amount of magnetic flux density, right? In other words, very high value for B for the same H value, right? For the same H value, there are materials which can give very high value of B, right? And also, for the same value, right? For the same value, for instance, let's say for silicon sheet steel, if you change the magnetic flux intensity, magnetic field intensity from 0 to a higher value, right, continuously, the variation is not linear, right? As you can see, the variation is not linear here. Linear in the sense it's not a simple line this. So it could have been a simple line this, but it's not a line, right? So if it was a line, this graph was a line, then this relationship is we call linear, right? Now in this case, you can see clearly that this is not linear, right? And the variation would give rise to a curve like this. This we call the magnetization curve for this particular material. Magnetization curve. Magnetization curve. Right. So what is magnetization curve again? So the variation of magnetic flux density B, right, for different values of field intensity through a given material. So through a given material, in the sense, for silicon steel, sheet steel, you would have a separate different curve, and for cast steel, its own another curve, and for cast iron, a different curve. And for air, right? For air, because if you assume that there is no metal plate, only the air is residing, so you would get a simple line, right? And remember, for air, the magnetization curve is a line, right? In other words, the BH relationship for air is linear, right? Therefore, for other materials like this sheet steel and cast steel, etc., the relationship is BH relationship for these other materials, right? The most of other materials, others is not linear, in other words, non-linear. right? So they are not going to be lines, right? And now what we can do is we can define another term, right? So for an instance, if I take air, in this case, so as you know, okay, the variation is linear, and which means for a given value of h, for a given value of h, the relationship of b I can simply denote by using the y equals mx graph, right? So mx equation. So for this particular case, our y is the magnetic flux intensity, y-axis is the magnetic flux, sorry, density, B, and X is the magnetic flux intensity, which is H, capital H, right? And this constant, right? In other words, this gradient of this line, we give a special name, the permeability. Sorry, we give a special name, the permeability of the medium. Of the medium, right? So in this particular case, permeability of air, right? And as you can see, since this is a line, mu is always constant, right? And mu, for air, we give a special symbol for the mu, in other words, the permeability, that is mu naught. Permeability air, we always define as air or free space, right? Permeability of free space actually we define as mu naught, right? It's very much closer to the permeability of air. Now, this equation is again very much important, right? So you must highlight this one as well. B is equal to mu h, right? Let me rewrite it. B is equal to mu h, right? And for air, mu naught. So this mu here means the permeability of the medium is a constant, right? It's a constant value. And when you consider these other materials, right? Other materials like silicon sheet steel or cast steel, if you consider a smaller distance, right? Not all the way like, not a very large range like this from which has a variation of magnetic field intensity from 0 to 1000. But if you consider a smaller range, like from let's say 700 to 800, 700 to 800, right? Smaller range, you can assume the variation, right? Variation of BH curve, flux density in relation to this magnetic field intensity to be linear, right? Because it's for a smaller range, it's like a line, right? So in this range, you can assume the mu value is constant. So mu simply means the gradient of this line. So you can assume it is a line linear and for smaller range. So simply, if I summarize again, for smaller range, you can assume the magnetic field, magnetic flux density variation with magnetic field intensity to be linear for smaller range. But in reality, it is non-linear, right? or these other materials as well, right? So therefore you simply assume, okay, this is made of lines, right? So here as well, this part you can assume, okay, linear, and this is linear. From here to here, different line maybe, but again at this range, it's becoming highly non-linear. You have to consider really smaller ranges at this range, smaller parts. If you are assuming it's linear, you have to think of very really smaller ranges, right? Right. So I hope the idea is clear. If I want to, if you need an explanation in Sinhala, again, since this is an important part, let me quickly go through. මෙතනදි කියන්නේ magnetic flux density එකයි magnetic flux intensity කියලා එකක් අපි කතා කරනවා. ඒ දෙක අතර variation එකට අපි කියන magnetization curve එක කියලා. ඒතකොට flux density එක කියන්නේ phi unit area එකකින් යන magnetic flux ප්‍රමාණය unit area එකකින් යන එක තමයි මේ කතා කරන්නේ. ඒක ඒ සම්බන්ධය රඳා පවතින්නේ මේ කොයිල් එක තියෙන්නේ මොන මීඩියම් එක මාධ්‍යද කියන එක මත. එතකොට අපි මෙතන කරන්න යන්නේ මේ එක එක ස්ටිල් ප්ලේට්ස් වගේ ඇතුළට දාලා කොයිල් එක ඇතුළට දාලා බලන්න යනවා කොච්චර මැග්නටික් ෆ්ලක්ස් ඩෙන්සිටි එකක් දෙනවද එකම මැග්නටික් ෆ්ලක්ස් ඉන්ටෙන්සිටි එකට. ඒ කියන්නේ ඇම්පියර් ටර්න්ස් එකම ගානට ටෙස්ලා කොච්චරක් දෙනවද කියලා තමයි බලන්නේ. ඒකට උදාහරණයක් විදිහට මම ගත්තේ 200 ගන්න. එතකොට ඇම්පියර් ටර්න්ස් 200ට ඔයාලා දැම්මොත් කාස්ට් අයන් කෑල්ලක් මේක ඇතුළට ඔයාලට හම්බ වෙනවා 0.1 ටෙස්ලා. හැබැයි ඒක කාස්ට් ස්ටිල් නම් 0.2 ටෙස්ලා. හැබැයි සමහරක් මැටීරියල්ස් තියෙනවා සිලිකන් ෂීට් ස්ටිල් වගේ ඒවා. ඒකට ගොඩාක් වෙලාවට ගොඩාක් වැඩි අගයක් හම්බ වෙනවා. එකම ඇම්පියර් ටර්න්ස් ගන්නට ගත්තොත් සලකලා බලුවොත් මේ තුන අපි නිකන් කම්පෙයාර් කරලා බලුවොත් එයා දෙනවා 1 ටෙස්ලා. ගොඩාක් වැඩි අගයක්. එතකොට ඒක පළවෙනි කාරණේ. ඒ කියන්නේ මාධ්‍ය මත ඩිපෙන්ඩ් වෙලා ඇම්පියර් ටර්න්ස් ගාන අනුව ෆ්ලක්ස් ඩෙන්සිටි එක වෙනස් වෙනවා සහ සමහරක් මාධ්‍ය තියෙනවා සමහරක් මැටීරියල්ස් තියෙනවා ගොඩක් වැඩි ෆ්ලක්ස් ඩෙන්සිටි එකක් දෙනවා එකම ඇම්පියර් ටර්න්ස් ගාන. ඊළඟ කතාව තමයි මැග්නටයිසේෂන් කර්ව් එක කියන්නේ. ඇත්තටම ගත්තොත් මේ එක මැටීරියල් එකකට ඇම්පියර් ටර්න්ස් ගානත් එක්ක ටෙස්ලා වෙනස් වෙන විදිය අඳින කර්ව් එකට. උදාහරණයක් විදිහට කාස්ට් අයන් වලට මැග්නටයිසේෂන් කර්ව් එක කියන්නේ මේක, කාස්ට් ස්ටිල් වලට මේක, සිලිකන් ෂීට් වලට මේක. ඒ කියන්නේ මැටීරියල් එක මත කර්ව් එකක් වෙනවා. හරි. ඒ වගේ ගත්තාම අපි වාතයට නැත්නම් ෆ්‍රී ස්පේස් එකට අපි යන්නොත් එහෙම කර්ව් එක ඒක අපිට හරියට මෙන්න ලයින් එකක්. ඒකින්ද අපි කියන රිලේෂන්ෂිප් එක ලීනියර් කියලා. ඒක රේඛීයව තමයි වෙනස් වෙන්නේ. හරි. එතකොට ඒක ලයින් එකක් නම් අපිට ඒක කියන්න පුළුවන් y = mx කියන ඉක්වේෂන් එකෙන් කියන්න පුළුවන් සරලවම. එතකොට මෙතනදී y වෙන්නේ ටෙස්ලා ගාන නැත්නම් ෆ්ලක්ස් ඩෙන්සිටි එක, x වෙන්නේ ඇම්පියර් ටර්න්ස් ගාන. එතකොට මේ m කියන්නේ අපි දන්නවා මෙන්න මේකේ අනුක්‍රමණයට නැත්නම් ග්‍රේඩියන්ට් එකට ඒ ලයින් එකේ. එතකොට මේ ග්‍රේඩියන්ට් එකට අපි විශේෂ නමක් දෙනවා මෙතනදී. ඒක තමයි permeability කියලා. permeability. ඒ permeability කියන එක සාධකයක් වෙන්නේ මෙන්න මේ මාධ්‍යයට අදාළ සාධකයක්. එතකොට වතුරට අදාළව එක permeability හිකුත් වාතයට අදාළව එකකුත් මේ එක මාධ්‍යයන්ට අදාළව වෙන වශයෙන් permeabilities තියෙනවා. එතකොට මතක තියාගන්න ඕන කාරණේ තමයි මෙන්න මේ සිලිකන් නැත්නම් මේ අනික් සමහර මැටීරියල් ගොඩක් මැටීරියල්ස් වලට ගත්තාම මේ variation curve එක linear නෙමෙයි non linear. මේක non linear. ඒක රේඛීය වෙනස් වීමක් නෙමෙයි. මේක ඇත්තටම මේ වෙනස් y = mx කියලා දක්වන්න පුළුවන් එකක් නෙමෙයි. ඒක නිසා මේක non linear. එතකොට වෙන්නේ මොකද්ද? එහෙම ඒ වගේ අපි කුඩා දුරක් ගත්තොත් ඒ කියන්නේ රේන්ජ් එක මෙන්න මේ ඇම්පියර් ටර්න්ස් ගාන වෙනස් වෙන රේන්ජ් එක අපි පොඩි අගයක් ගත්තොත් අපිට උපකල්පනය කරන්න පුළුවන් හරි මෙතන ඉඳන් මෙතනට මේක ලයින් එකක් කියලා. ඒක අපේ උපකල්පනයක් විතරයි. එතකොට assumption එකක් කරද්දී වර්ධින ඒ කියන්නේ දේවලුත් වෙන හැබැයි අපේ අවසාන ප්‍රතිඵලයට ගොඩක් බලපාන්නේ නැහැ මේ assumption එක. හැබැයි මේ වගේ තැනක් ගත්තොත් මම මෙන්න මෙතන ඉඳන් මෙතන රේඛිය කියලා ගත්තොත් ඒක ලොකු එරර් එකක් එනවා. ඒකින්ද ගන්න ඕන ගොඩක් පොඩි දුරවල්. ඒ කියන්නේ මෙන්න මේ වගේ මෙතන එක දුරක්. මෙතන තව දුරක්. ඒ වගේ පොඩි දුරවල් අරගෙන මට මේක ලීනියර් කියලා හිතන්න පුළුවන්. එතකොට කියන්න ඕනේ එහෙනම් මෙතනත් ලයින් එකක් තියෙන. ඒ කියන්නේ ලයින් එකක් y සමාන mx ආකාරයට එතනදිත් අපිට ප්‍රකාශ කරන්න පුළුවන්. එතකොට මේ ඕනම වෙලාවක මේ ඕනම කර්ව් එක මැග්නටයිසේෂන් කර්ව් එකේ ඕනම තැනකදී ග්‍රේඩියන්ට් එකට නැත්නම් අනුක්‍රමණයට ඔයාලා දන්නවා ඕනම තැනකදී ග්‍රේඩියන්ට් එකක් අපිට අඳින්න පුළුවන්. දැන් මෙතන ගත්තාම ග්‍රේඩියන්ට් එක මෙහෙම මේ වගේ පොයින්ට් එක මෙහෙම වෙනවා. මේ වගේ පොයින්ට් එක මෙහෙම වෙනවා. මේ ඕනම වෙලාවක මේ ග්‍රේඩියන්ට් එක තමයි මේකට අදාළ මියු වෙන්නේ. හරිද? නැත්නම් පර්මියබිලිටි එක වෙන්නේ. එතකොට කාස්ට් සිලිකන් ෂීට් වල ගත්තාම නැත්නම් කාස්ට් ස්ටිල් වල ගත්තාම non linear නිසා ඇම්පියර් ටර්න්ස් ගානත් එක්ක මියු නැත්නම් පර්මියබිලිටි එකත් වෙනස් වෙනවා. අපි කතා කරමු A කියලා පස්සේ පර්මියබිලිටි එකත් වෙනස් වෙනවා. හැබැයි එයා වගේ කෙනෙක් ගත්තාම එයා ලීනියර් හැමතිස්සම මැග්නටයිසේෂන් කර්ව් එක H එක B වෙනස් වෙන විදිහ හැමතිස්සම ලීනියර්. ඒක නිසා gradient එක constant. ඒ කියන්නේ එයා වගේ දෙයක් ගත්තාම එයාගේ permeability එක හැමතිස්සම constant. මම හිතන්නේ පැහැදිලි. ඊළඟට කියන්න ඕන දේ තමයි හැමතිස්සම එතකොට හැමතිස්සම නැති වුණත් දැන් ගොඩකට අපි linear කියලා සලකන region වලදී අපිට පුළුවන් b සමානයි mu h කියලා value එක මේ equation එක apply කරන්න. හරි. මේක තමයි මාධ්‍ය permeability එක. මේක තමයි ampere turns ගාන. මේක තමයි Tesla එක. ඊළඟට අපි තව දෙයක් define කරනවා. ඒ තමයි relative permeability. එහෙම නැත්නම් සාපේක්ෂව ගත්තාම mu ගේ value එක. ඒක හොයන්න අපි කරන්නේ අපි හිතමු සිලිකන් ෂීට් කියලා සිලිකන් ෂීට් වල mu value එක mu ss නම් අපි බෙදනවා වාතයේ mu value එකෙන්. ඒතර වාතයේ mu value එක වගේ කී ගුණයක්ද කියන එක තමයි relative permeability කියන්නේ. So in order to define relative permeability, what we do is we take the relative permeability of the medium and divide it by the relative permeability of the free space, right? So that will give you the relative mu value, right? Or it's the relative permeability value. So this is a very simple equation. Mu r is always this mu naught is a constant. So we are dividing by a constant. This means the permeability of a given medium. So in this case, the silicon sheet is steel. For cast steel, it's a different mu value. So depending on that, the relative mu value would also be different, right? I hope those are clear. And let's discuss again about the relationship with the theory behind this magnetic flux and magnetizing force. In other words, magnetic flux, magnetic field intensity. How this type of curves are made depending on the atomic scale or as the molecular scale arrangement of different materials. So it all begins. This is just a theory defined, theory kind of created to define this variation. So for an instance, if you take a piece of, let's say, silicon steel. Now this is a silicon sheet steel plate. Now we assume there are, this is made of molecules, right? So we assume there are smaller molecules, right? Molecules in the sense in the level of atoms, right? So molecules are made of few atoms. I hope you already know that. So we define a special type of molecule which is a magnet, right? Very small molecule, so which has north and south pole, right? So usually if I kind of draw an enlarged shape, so it's something like this, right? It has a north pole and south pole, and we assume there are something known as these molecular magnets, or else the same we give a name, domains, magnetic domains, right? Domains, or as molecular magnets, right? We assume that this sheet is made of these domains, right? There, in other words, there are domains, thousands of domains in a given plate, right? Piece of plate, right? Now, to denote this magnetic flux of this domain, I'm going to use simply an arrow, right? So this, for this particular domain, it's in this direction, right? Now from here onwards, I am only considering about this field direction, right? Field direction. Now in some materials, right? In some materials, these domains are arranged in the same direction. So which means the summation of these fields would give a resultant magnetic field, right? So in that case, what would happen is those materials are always going to have a magnetic field around them, right? Such materials, right? Such materials we call permanent magnets. They are permanently showing the magnetic properties. Permanent magnets, right? So domain කියලා જાතියක් ගැන අපි හිතන් ඉන්නවා පොඩි අංශු වගේක් මේ වගේ magnetic properties තියෙනවා පොඩි කාන්දම් කැලි කියලා හිතමුකෝ එහෙම හිතුවොත් ඒ කාන්දමක තියෙන magnetic field එකේ direction එක මේ ඊතලෙන් පෙන්නනවනේ දැන් මෙතන මේ මම පෙන්නලා තියෙනවා sorry for the disturbance. මෙතන මම පෙන්වලා තියෙන්නේ molecules නැත්නම් magnetic domains පහක field direction එක. මේ පහේම fields එකතු වෙලා ලොකු field එකක් හැදෙනවා. එතකොට හැමතිස්සෙම මේ atoms මේ විදිහටම තියෙනවා නම් නැත්නම් sorry මේ domains මේ විදිහටම තියෙනවා නම් magnetic field එක හැමතිස්සෙම තියෙනවා. අපි ඒවට කියනවා permanent magnets කියලා. Right? So for some other materials, right, the domains are arranged in a way like this, right? So in that case, what would happen is, you know from vector summation theorem that when you have vectors arranged in a closed shape like this, the resultant vector is 0. So for such materials, they don't have any magnetic properties, non-magnetic, right? So that's why we don't see magnetic fields around some materials called permanent magnets and other materials which we don't see any field around other materials as non-magnets, right? And for some other types of materials like ferromagnets, what you have is something called as, again in nature the domains are arranged in closed shapes like this, but once you apply a magnetizing force externally, right, what would happen is these domains are going to arrange in the direction of this magnetizing force. So making it able to propagate this magnetizing force, or as the magnetic field intensity, forward, right? So that is what it is happening in this silicon sheet steel. So in the silicon sheet steel, what is in nature, so if you take a silicon sheet steel, right, in nature they don't show any magnetic properties, nah, right? The domains are arranged in closed, randomly arranged in closed shapes, right? Then what would happen is, once you apply a magnetic field intensity externally, that's what this coil is doing. It's giving an edge to this material, right? This piece of SS, right? Silicon sheet steel. Now, what would happen is because of this external magnetic field intensity or as magnetizing force, we use both those terms. These domains are going to arrange in the direction of this field, external field, right? And they are going to rearrange within the material itself, right? Now what you have is some magnets in the same direction. Therefore, now you have a resultant field, right? So, which means you can propagate this magnetic field forward, right? Now that is what is happening here. So when you apply a, let's say, okay, if you start from the ampere turns 0, right? 0, initially it won't show the magnetic field value would be zero, yes, the magnetic flux within the material would be 0, right? And when you apply a higher value, right, some of the domains would arrange, in the direction of this external field, but there would be still some other domains which are still not arranged, right? Let's say there are 100 domains, right? Maybe 1,000 domains. At a point like this, only let's say 700 domains are going to arrange in the direction of field, and the other 300, right? Other 300 is going to be randomly arranged as it was before, right? But still, this would give rise to a net magnetic field, right? Magnetic flux within the sheet. So there would be a B value, right? Now, when you increase, what would happen is, let's say you are going to increase this to 400. Out of this 300, domains, another maybe 200 would be rearranged in the direction of, so you are increasing the intensity now, would be rearranged in the direction of field intensity, right? And what is the reason for this declining of at the end? The reason behind is, at a point like this, you are going to use all the magnetic domains it has. So once all the 1,000 domains are in the direction of magnetic field, right? When all the 1,000 domains are arranged in the magnetic field, right? No matter how hard you try, or else no matter how much you increase the ampere turns, there are no molecules to rearrange in this direction. So the flux would remain constant, right? The flux would remain constant. So because all the domains are now arranged, and even if you have increased the H value here, there are no domains to rearrange. Therefore, the flux would be the same, right? That's why this curve is going to decline at the end. Now, this special situation we call as the saturation, right? Saturation of this material, saturation. සම්තෘප්ත වෙනවා. තියෙන සේරම අණු ටික ඒ පැත්තට නැක්කම් පැත්තට හැරුණාට පස්සේ ආය හැරෙන්න අණු නැති හින්දා මොකද වෙන්නේ, magnetic field intensity එක වැඩි කරත් ටෙස්ලා ගාන වැඩි වෙන්නේ නැහැ. මොකද තියෙන ඔක්කොම අණු ටික ඒ පැත්තට හැරලා ඉවරයි. ඉතින් ඒකින්ද intensity කොච්චර වැඩි කරත් තේරුමක් නැහැ. flux level එක constant වෙගෙන යනවා. හරි. මේ වගේ තැනක් ගත්තාම උනේ මොකද්ද? මේ වගේ තැනක් ගත්තාම magnetic field intensity එක තියෙන පැත්තට intensity එකට සාපේක්ෂව යම් ප්‍රමාණයක් ඒ පැත්තට හැරුණා. තවත් ප්‍රමාණයක් හැරෙන්නේ නැතුව අර රැන්ඩම් arrangements වල නියුට්‍රල් වෙලා ඒ විදිහටම හිටියා. ඒක නිසා එහෙම නියුට්‍රල් පොසිෂන් එකේ නැත්නම් net magnetic field එකක් දෙන්නේ නැති පොසිෂන් එකේ තියෙන අණු 100ක් විතර තිබ්බා. එතකොට ඒක නිසා BLU එකක් ආවා. හැබැයි තවදුරටත් ඉන්ටෙන්සිටි එක වැඩි කරද්දි B වැඩි වෙන්න පුළුවන් වුණා. ටෙස්ලා ගන්න වැඩි වෙන්න පුළුවන් වුණා. හැබැයි මේ වගේ තැනකදී සැචුරේට් වෙනවා. සහ කර්ව් එකේ එන්නම ඩික්ලයින් වෙන හේතුවත් පැහැදිලි. මොකද තියෙන ඩොමේන්ස් ගන්න එන්න අඩු වෙනවා. So this is the kind of the theory, molecular theory of this magnetic, the relationship between magnetic flux density and the magnetic flux intensity and field intensity, B and H variation, BH curve. So, but you should know that this is not the kind of the way that science would define magnetic flux properties of materials. Now we have something called as a spin electronics theorem, spin electronics, and of course it's about the kind of the orbital and spin movement of the electron. So you can orbital plus spin movement of electrons. So if you want to know more about it, and then it's something related to quantum physics, and that's how the modern science is defining magnetic fields. So the one I used is kind of a old way of defining magnetic fields of materials. So the modern way you can find out by yourself, which is kind of not that much needed for our topic of electrical machines theory. I'm not going to discuss, so this is not in our scope, so I'm not going to discuss it therefore. But if you want, you can find more and read more about that, right? So remember that as well, right? From here, I'm going to give you a break of 10 minutes, so you can charge your phones. We can meet again by 10:25. If you have any questions, you can ask now. I'm going to end the meeting and start it again by 10:25. So if you have any questions, you can ask. I'm going to end the meeting and start it again. So please be back by 10:25.